Yes, sir. Assalamu alaikum, everybody. Thank you so much for joining us, and thank you so much to sir for joining us. मैं बहुत मशहूर हूँ सर का कि सर ने आज हमारे लिए वक्त निकाला। सर अली अकरम, अगर मैं कुछ टीचर्स को जानता हूँ तो उनमें से सबसे ज़्यादा मेहनती टीचर्स में से एक सर अली अकरम है। और मैंने आज तक कोई स्टूडेंट ऐसा नहीं देखा कि जो सर से सेटिस्फाइड ना हो या सर ने उसको हेल्प ना किया हो ए लेने में, चाहे वो डी पे है। सर ने उसका ग्रेड बदला है और कई तो मुआवजे भी किए हैं सर ने इस लिहाज से। तो मैं बहुत मशहूर हूँ, बहुत मरहूने मिन्नत हूँ सर का कि उन्होंने वक्त निकाला हमारे लिए आज के दिन में when he's so busy inundated with so many questions. So yeah, without further ado, let's hear it from Sir Ali Akram.
Thank you so much, Sir. Okay, everybody will be beginning with a very initial chapter, that is the binary number system, since it's a division class. So I'll be focusing on the key areas. Everybody will be beginning with a very initial chapter, that is the division class. So I'll be focusing on the key areas. Okay, so we can start with binary number systems. Okay. When we talk about binary and we do not, if we don't talk about binary number system, then it doesn't fulfill the purpose. Okay, there was a question in past papers in which you were asked that you were required to compare the two number systems, and it carried around 4 marks. So as you all know that whenever we are asked to distinguish certain two quantities, in this case it is binary, and in the other branch we can say it's denary. So we can compare the two number systems by looking upon very basic differences between the two, and I will be guiding you how you can answer such questions. So when we talk about binary, basically binary is base 2, whereas denary is base 10. It involves digits from 0 to 1 or 0, 1. Similarly, for denary, we can say that it involves digits from 0 to 9. So it accumulates to 10 values. So you can also derive one other difference between binary and denary. We can say that it only involves 2 values in binary, whereas in 10 values in denary. We can also say used by computer. You can also say used by humans. Then one major difference which I would like to present to you is that the positional significance. So if we say positional significance, of digits increases in power of 2 from right to left. Similarly, we can also say the positional significance of digits increases in power of 10. So when I say that positional significance, you all are aware of these positional values like 1, 2, 4, 8, 16, 32. So let me tell you a logical background of this. This is 2 power 0 because 2 is the base 2. So therefore, this is the position. This is 2 power 1, this is 2 power 2, this is 2 power 3, this is 2 power 4. So as you can see, from right to left, the position significances are increasing. So whereas for Denry, it is 10 power 0, 10 power 1, 10 power 2, 10 power 3. So in childhood, you might have encountered this. This is known as unit. This is known as 10, this is 100, this is 1000. So these all are positional number systems. So therefore, when we say that Denry is a positional number system, that means each digit has its own positional significance, which increases from right to left. Okay. I will not be particularly devising the conversion section because I'm aware that most of you do know how to convert certain values from one number system to another. So I won't be focusing on that portion. However, if you do have any questions regarding to that, so you can ask me, no problem. However, I'll be focusing on the key areas which students actually lack in. So therefore, we can keep a focus on those areas well. Secondly, there was another question in past paper that was actually the part B of this question that we just discussed. So the question stated that you were given a number of 1010, that is of course binary, and you were asked to describe how you can convert this number to Denry. Okay, in order to convert that, all of you do know that this is a very small binary number. You can easily put 1, 2, 4, 8 on top of it, and you can add 2 and 8 to become 10. But in this question, we have been asked to describe. So you must be well aware that whenever we are asked to describe certain thing, whenever we are asked to explain certain thing, so you have to answer it in a different way. The major reason that students lose their points in exam is because they do not pay attention to the first word written in the Cambridge question. You must be aware that in every Cambridge question, there is a keyword. If you have a state, it carries a different meaning. If you have a give, it carries a different meaning. If you have an explain or describe, it carries a different meaning. So how can we describe this whole procedure? So we can comment, we can start by commenting on what is a binary number system, and we can talk about the positional significances, and then we can come to this number given. By referencing to this number, we can actually add the values where we have a 1. So whatever I have just put forward to you in discussion, I'll be putting it in writing now. So what I will say, binary is a positional number system in which each digit has a positional significance that increases in power of 2 from right to left. Now remember, this question is of 5 marks, so it should be answered accordingly. So therefore, from right to left, as 1, 2, 48. So you can write the values as such: 1, 2, 4, 8. The given number can be converted by adding positional significances where we have a 1 bit. That means an on bit. Okay. So for example, 1010, and we'll be writing 1248. So this is 8 plus 2, and that will be 10. So this is your complete answer to that question. Okay. If you have any questions, let me go through it. Okay, sure. I can scroll up, Harun, no problem. Okay, we'll revise input and output as well. I'll be paying attention to the conversion part because some of the students approached regarding the conversions as well. So I'll be revising the conversion section as well. So I think that those of you who wanted me to scroll up, they might have noticed it. Okay, sure. Now we can move forward. And some of these students asked a question regarding HTML color codes. Now, please remember that, let me put it in a different marker. Like in exam, you are asked to write down users of hexadecimal. And students tend to write HTML. This is wrong. Okay, this is wrong. You have to write HTML color codes because it is the color codes which actually use the hexadecimal notation in order to describe a certain set of colors. So how can we do that? Usually we have 24 bits. So out of these 24 bits, we can make a division of 8 bits, 3 divisions of 8 bits. So these 8 bits can construct up to 2 hexadecimals. And I am sure that most of you will be aware that when I'm saying that we have 8 bits and 2 hexadecimal values can be constructed from those. So it must be clear to all of you. 2 hexadecimals. Then again, 2 hexadecimals. Then again, 2 hexadecimals. So let me construct the placeholders for these. So we have 6 hexadecimal digits to express one color value. Okay, since we began with 24 bits, that certainly means that there are 2 power 24 color values available to choose from for 1 pixel for 1 pixel color. Yes, absolutely. Whatever we are discussing right now, everything is in our syllabus. Yes, nothing beyond it, nothing below it. So we have 6 hexadecimals. So if we say that the first 2 are for red, then the next ones are for green, and the next ones are for blue. So as you all know that each can have a value from 0 to F. So if we say it's a 0, that means it's the darkest side. That means we are moving towards blackish shade. However, when we say it's an F value, that means it's the brightest side and it's the brightest shade that we are talking about. So if I say that only the 2 hexadecimals allocated for red are on and green is off, blue is off, that means it is purely red and it is the brightest red that is possible that can be expressed over here. So therefore it is the red color that will be generated. Over here, no contribution from green, no contribution from blue. Similarly, we have 00 FF 00. That will certainly state that we are considering only the green color over here, and green is present in its full strength, nothing left behind. Okay, and no contribution from blue, no contribution from red. So therefore, this color will be purely green and it will be the brightest green. Okay. Then we have 0000FF. That means we are only considering the blue portion over here, and both the hexadecimal values are having the extreme value, the maximum value that is possible. So therefore, it is the blue shade and it is the brightest blue. Okay, there was a question in the past paper in which you were asked that how different shades of colors are possible. In that question, you were given an example, like it was just for an example. Like you weren't asked to mention how you will generate the darker shade of blue. No, it was just given as an example. So you only had to state that how different shades of colors can be generated using these 6 hexadecimals or 24 bits. So therefore, as an answer, what you could have written is that a new or a different color value can be generated by changing of any hexadecimal digit from 0 to F. For instance, A5 of FB06 is a different color shade from A4 FC15. Okay, so you can vary any of the hexadecimal values and it will be a new color value. So actually, no, we will be trying to cover most of the areas. You can forward me your problems so that I can answer them appropriately. Okay, from here, I'll be moving to the image size calculation and sound file size calculation part. So let's consider doing file size now. So I will try to cover most of the topics that you have sent to me in your chats. Okay, just give me a second. It will be just okay. Considering the file size now, images. When we say we have a bitmap image, so there will be some width, there will be some height, there will be some colors or color depth. So if you are provided colors like 256, so you will have to calculate your color depth on your own. However, if you are provided color depth like 8 bits. So no need to go upward and calculate the range of colors. Okay. Having said that, let's construct our own question first. Let's say we have an image of 2000 pixels as width and 1000 px as height, and let's say the color depth is 8 bits. So let's construct it. So image file size is equals to width into height into color depth. And since your answer is required in, let's say, megabytes, so we can consider that calculation then. Okay, we have a width of 2000, we have a height of 1000, we have a color depth of 8 bits, and in order to convert it into bytes, we can divide it 8. And also, in order to convert it into kilobytes or megabytes, we can consider a map that I'll be drawing over here. Okay. So in order to convert it into megabytes, we'll be dividing it first with 1000 so that it converts it into kilobytes. And then we have another 1000 over here. So without calculator, how you can work with this, it's very clear cancellation process that can be deployed over here. So you can see this 1000 can be cut with this one and everything. One mistake that students usually do is they tend to calculate the numerator first, and then they also tend to calculate the denominator first, and then they perform calculations, and by cutting these values, which is totally problematic, and it consumes so much time. So therefore, what you can do, you can keep on writing, like you can keep these values as such without any multiplication or without solving the numerator separately or denominator separately. So now you can see, you can just divide these values with this one and you will be getting 2 MBs over here, 2 megabytes of the image. One question that I have been asked multiple times, that what do we have to choose for denominator? Can it be 1000 or can it be 1024? According to the FAQs from the Cambridge, they actually do prefer that you tend to use 1024. But in that case, since you do not have, okay, it's Azan time. I'll be just back online in 1 minute. Okay, so we are back. So over here, I was telling you that what to use, 1024 or 1000. According to the Cambridge FAQs, you can use, you should prefer to use 1024. However, if you do have such values in numerator, you can go with 1000. It is totally permissible. Your marks won't be deducted. Let me give you an example how we can convert such values. Let's say we have 2048px as our width. and 1024 px as our height. And then once again, we can consider 8 bits as our color depth. So doing this question once again, that will be 2048 multiplied by 1024 multiplied by 8, and then dividing it with 8 first, and then 1024 with dividing it with 1024 twice. So therefore, you will be getting your answer, and that will be quite similar to the above given above. Okay, considering the sound file size, let me give you another example over here. For sound, we have various terms which I was inquired about today. So we have for sound, you should be actually, whenever you are asked to define how a sound is actually encoded. So you have to begin with microphone first. Whenever you speak into microphone and what happens after, only 1 or 2 lines for that. And after that, you have to come to these 3 terms, which are sample rate, which is number of collected per unit time. It is usually measured in hertz or in per second also. And then we have bit depth. So you should be able to answer it as well. Number of bits per sample. Like if your sample is of 2 bits, so your bit depth would be of 2 bits. Then we have sampling. So it is the process of collecting amplitude values at regular intervals of time. So considering this, if we are asked to find out size of a sound file, how we can do that? We can simply multiply the sample rate multiplied by the bit depth multiplied by the number of seconds and usually number of channels for speakers. Okay, considering this, if this answer, like our bit depth is in bits, so this answer will be in bits. If bit depth is being considered in bytes, so our above answer will be in bytes. So let me discuss with you an easy trick how you can operate with these. Yes, Vita, I will share these notes, no problem, no problem. Okay, so considering this, we can talk about, we have the smallest unit that is bit. We also had a past paper question regarding this, covering this whole hierarchy, that is the map that I'll be drawing before you. So from bit to byte, and then we have KMG, you have to memorize this, KMG TPE. So it is KMG TPE. Once again, KMG TPE. Okay, so considering this one, if we want to go from bit to byte, we have to divide it with 8. That is static. You cannot change that. Okay. But however, from this level up, if you are going from aiming to go from byte to kilobyte, you can choose 1000 depending upon the numerator values, whatever you are given, or you can also choose 1024. That is totally fine. So as you all are aware that 1000 is basically 10 power 3 and 1024 is basically 2 power 10. This one value that I have just written is extremely crucial while you are solving without calculator, because in tomorrow's exam you are going to be without calculator there. So this whole value is going to help you in order to solve certain calculations. So therefore, from here upward, once again, you can divide it with 1000, 1000, and so on and so forth. So this whole thing is 1000. Okay. So if we want to convert certain quantity from bits to, let's say, gigabytes. So I am sure that you must be aware that small b means bits and capital B means byte. So however, we want to convert bits data into gigabytes. What we can do, we have to first travel from bit to byte and then upward. One step, two step, three step. Once again, from byte to gigabytes, one step, two step, three step. So what we can do, we can first divide it with 8, and then we can continue dividing it with 1000 power 3. Why? Because we are at bytes, and in order to go into gigabytes, we need to travel 3 steps. So therefore, it is power 3. So therefore, it is very easy. If you want to go in order to convert from byte to megabytes, how many steps? 1 and 2. So therefore, 1000 power 2. However, if you want to go with 1024 part, you can easily choose 1024, and then powers will remain same, just like the number of steps that you are utilizing. Okay, I hope this clarifies it. Now I will be moving to the logic gates portion. Okay, we have certain gates available to us, and I'm sure that most of you will be aware of the gates that I'll be drawing before you. This is a NOT gate. This is an AND gate. Okay, let's draw it more. So this is an AND gate. This is an OR gate. Similarly, this is a NAND gate with a bubble, and therefore we have another gate that is the NOR gate. And then last that is being considered is the XOR gate. Okay, all of them except NOT gate have 2 inputs and 1 output. So whenever you are asked to describe certain gate, which you were asked in around 2017, I think, yes, and you were asked to describe the functioning of XOR gate. So how you can comment on that? You have to begin by telling about the 2 inputs that we have and an output that we will be producing. And then you have to describe the behavior of this logic gate. That is, whenever we have an input of 0, 1 or 1, 0, the output will be 1, otherwise it will be 0. Okay, that is totally fine. So considering this one, let me bring forward to you onto your screens a question regarding the logic gates. But please let me know if you have any issues with logic gates. Otherwise, we can skip it for now. Yes, Peter, building blocks are there, but you might be asked about them. So you should be aware of them. Okay, so I think everybody is okay with logic gates, so we can skip this portion. No problem. Okay. Okay, somebody wants me to discuss the building blocks. Okay, we can discuss them. So building blocks are usually constructed through NAND and NOR gates. So in order to construct a NOT gate using NAND gate, how we can do that? As you all know that a NOT gate actually has only 1 input. So therefore we can begin with 1 input, that is A. Now we can subdivide this connection into two and give it to the NAND gate. And this will be our NOT gate using NAND. Similarly, using NOR gate, we can also deploy the NOT gate like this. Okay. So let me tell you how we can arrive at this NOT gate. Okay, sure. So over here we have a, and then again, since this is the same branch, so we'll be having another A over here. And now you can see this can be written as A dot being and once again A and whole not. So A dot A becomes A, and then you get A not over here. Similarly, you get your A over here. A is supplied in this branch, A is supplied into this branch. Then we have A plus being OR gate, and then whole not. So A plus A is again A, so this will be A not. So therefore A gives you A not, A gives you A not. So that means it is successfully functioning as a NOT gate. Okay. Then we have NAND gate used to deploy an AND gate. How we can do that? We can begin by doing NAND of A and B. That will give us A dot B whole not. Once again, we can subdivide this branch into two so that it becomes this NOT gate. So it will become, since this is now functioning as a NOT gate, so A dot B whole not will become A dot B afterwards. Okay. So similarly, you can see that from using NOR gate, how you can deploy an OR gate, sorry, an AND gate. This is your A, and it will become A naught. Similarly, this is your B. And using this approach, it will become B naught. So we'll be merging these two using a NOR gate over here. And what they will become. So they will become A naught plus B naught and whole naught. So if you solve this, it will become A dot B. That is actually the rule that you can focus on. No, let me write it down. So dot or asterisk means AND gate, and plus means OR gate. Yes. Okay. So that is fine. So you must be aware in a question given in past paper, there was a question in which you were given this assembly and you were asked to comment which gate it was. So it carried 3 marks. So if you knew this assembly, you can definitely mark it correct and do the thing. And you can write down your output as that of an AND gate because this is your AND gate. Similarly, you were also given an assembly like this in the same question. This is your A naught. And similarly, if we talk about B over here, so this is your B naught. So we can merge these two into another NAND gate. And it will be A naught dot B naught whole naught. So it will become A plus B. So I have used these Boolean algebra symbols because otherwise if I would have written AND or NAND in spellings, it would have occupied a lot of space and I didn't want to confuse any of you. Okay, so considering this one, if we want to construct an OR gate using NOR, then that's the last one. So let's do it together. This is your NOR gate and A and B are being supplied to it. And once again, we can deploy another NOR gate over here and it will construct A plus B. Okay, that is fine. If you want to memorize it, let me tell you a trick to do that. Okay, so AND can be deployed using NAND, using 2 NANDs. Similarly, for OR gate, if we want to deploy it through NOR, so 2 NORs will give you 1 OR. 2 NANDs will give you 1 AND. Similarly, this can be considered as opposite, like this, and this can be considered as opposites. Okay, so this can be easily memorized then. Okay. Having said that, let me continue to the next topic. Okay. So now we'll be moving to the fetch, decode, execute cycle. So the first thing is that, let me give you an example. Let's say we have these instructions written in our immediate access store. Let's say we have 17, we have address 18, we have address 19. So this is the address, and over here data slash content. So let's say we have content like 87, 90, and then again we can write some dummy value like 11 over here. Okay, so this is the next instruction that needs to be fetched. So therefore we have a register whose duty is to remember the address of the next instruction to be fetched. So this is the address that needs to be fetched. So therefore there is a register which will be containing the address of this instruction that needs to be fetched. Fetch means mangwana. That means hum log kuch mangwana cha rahe hain. That means the processor wants to fetch these instructions so that it can process it. So therefore PC contains the address of next instruction. Once it tells to the MAR that this is the address, ये हमारा पहला step हो जाएगा. So once it tells to the MAR that this is the address, so the duty, technically, the duty of PC is fulfilled. Now its duty is to remember the address of next instruction to be fetched, that is the 18. So therefore, instead of 17, it will now have 18, and this will be your second step. Okay. In some of the books and some of the past papers as well, this step of incrementing PC has taken place just before the loop restarts, like from the bottom again. This PC is equal to PC plus 1 has taken place at many other steps. So let me tell you that this step of PC is equal to PC plus 1 can appear anywhere once the address from PC into MAR has been copied. So it can appear anywhere. It's totally fine. So you can go with any of the approaches, but only make sure that this step of incrementing PC does not take place before the address of PC, the address contained by PC is copied into MAR, not before that, only after that. Once we are done that, we are safer, we are on the safer side, so we can increment PC. So once we have done that, now we can move on and copy this as third step, the data corresponding to the address in MAR, that is MAR contains 17. So therefore data corresponding to that is 87. So MDR is the register that will be containing the value. So this whole value, the content that is located at that address, that can be some instruction. So it has to be decoded afterwards. So therefore, as our fourth step, we can move this data or copy this data into CIR. So this completes our fetch stage. So you have to be aware. If you are asked in exam that you have to describe the fetch process, this must be your answer. Do not include any decoding part. Do not include any execution part. You have to describe the fetch part. Okay, moving forward now. After that, you can see that decode stage happens, and whatever we have fetched, we tend to decode it and tend to understand its meaning. Once we are done with decode part, we can begin the execution. So this is our final most stage. After that, we repeat. We repeat from start, and PC, we ask from PC, okay, what is the next instruction to be fetched? So it says, okay, it is 18. So we go to the 18 and the whole process repeats and PC gets incremented to 19. Okay. Yes, absolutely. Program counter is a register like CIR and BR, and it is special purpose register. Okay. Sure. Now we can move forward. And you can let me know of any other area. A bit of the reason is that at 17 we have 87. So therefore, MAR and MDR actually are working in couple over here. Okay, I'll be answering your question. Okay, so if MAR contains 17, MDR will contain 87. If MAR contains 18, MDR will contain 90, that is 90. Okay, Isa beta, are we clear about it? Okay, it's the control unit. Okay, so IAS is basically immediate access store. So any instruction that needs to be executed has to be brought in from the backing store into the immediate access store so that it can be fetched and decoded and executed. So let me tell you that at the decode stage, we are actually aiming to understand the meaning, understanding the purpose of that instruction. That what do we have to do with that instruction that has been just fetched. Okay, sure. I can repeat the fetch process, no problem. So over here we had a register of program counter. That means it has to keep count of the next instruction. Next instruction. That means इसकी duty यही है, इसने में next instruction का बताना है. So therefore, initially, according to this table, PC contained 17. Okay, so we started off with 17. Once the PC copied the address from PC to MAR, once this step was performed, so PC was now permitted to contain the address of next instruction. So now it will contain 18 instead of 17. So we incremented, like we increase the value of PC by 1. So therefore, PC is equal to PC plus 1. It will become. Okay, once it is done, so the data corresponding to the address in MAR, like if we have 17 in MAR, we'll be having 87 in MDR. If we have 18 in MAR, then we'll be having 90 in MDR. So once we have done that, from MDR into CIR, the data or the content is copied into CIR, and after that we decode. So some of you have asked that what happens at the decode stage. So decode stage involves understanding the meaning of the instruction that has just been fetched. And after that, once we have done that, we can execute it and we can perform whatever was required. Okay, so control unit is actually basically the coordinator of all the components. The signals that is passed, that is passes to different components actually help to coordinate the activity. It also fetches the instructions, whatever you have studied over here. Yes, Mikhail Beta, accumulator is actually used with ALU because ALU performs certain steps like the answer of addition will be momentarily stored in accumulator. So it is associated with ALU, yes, definitely. But accumulator stores the values of calculations temporarily before they are overwritten by the new values. Okay, is there any other question? Please let me know.
थैंक यू सो मच सर।
You are most welcome, sir.
बहुत यूजफुल और बहुत हेल्पफुल सेशन था, आई एम श्योर। और अगेन बहुत नवाजिश के आप आए।
Thank you so much, sir.
इंशाल्लाह इन बच्चों के ग्रेड्स बहुत अच्छे आएंगे।
Inshallah,
और
sir.
आपका नाम भी
And
रोशन करेंगे इंशाल्लाह।
my best wishes for them. Inshallah.
थैंक यू सो मच सर।